Okay, so let us start. I would like to make an announcement first. You might have received the email by Andrea already. So we wanted to delay the deadline for projects to make it easier for people to do them. And I want to stress again that these projects should be not an excessive amount of work. I mean, they're built on this course. They should correspond to something that's maybe, think of 2 exercise sheets, something of this form. And they can be more theoretical or they can be more practical. So a more practical project would be more on the side like I invest some time to model a system and to optimize it in some form or the other. Yeah. So I don't want to give ideas, but something that's maybe a bit more challenging from the optimization, from the modeling perspective. Yeah? And the other way would be that you just take, for example, one of the models that we did in our lecture already, and you just say, I want to investigate this method, which was presented or mentioned, or maybe not even mentioned, but where we never did an exercise about. And then you basically invent your own exercise sheet with a given model. And I want to investigate the pseudospectral control method, or I want to compare this and that method. So there could be simple things. Yeah? One could also investigate something theoretical. Yeah? So we could discuss, and there is some individual freedom, full freedom actually to choose something. That's what the projects are designed to. Maybe I should also mention that historically the projects came out of the problem that I had, that I want to make this lecture available to both engineers and mathematicians. And mathematicians for a lecture course of this size get 9 ECTS, engineers get 6 ECTS for something with this amount of lectures and exercises. And in order to bridge the gap, we introduced the projects, which are optional for engineers. I don't say more words, so the rest you have to add in your head. So the project formally accounts to 3 ECTS. Okay, is there a question? Yes.
So there will be still a presentation?
Yes, exactly. So what we delayed, so the deadline. So what is the project deadline? The deadline is now August 17. What we would like to have by then is a finished project, so no work afterwards, and there will be a short presentation. So think of something with 5 slides. There could also be a Blackboard presentation, by the way. Short report. Also here, think of 5 pages. Of course, if you have computer code, then it should contain the computer code. And usually projects will have some computational code, but some might have more and some others have less. This is it. And the date of the presentation we will just make between those that really subscribe to projects. Which seems not to be such a large number, but I would hereby really like to re-invite you to do them. It's a relatively easy way to deepen your knowledge on optimal control.
So no presentations on Wednesday?
On Wednesday. That's a good point, because there will be some people that have already their projects, right? You, I think. Yeah.
Yes.
So Wednesday we will talk about projects. I will actually maybe do a 1-hour lecture summary because we don't have so many projects. So we have a lecture summary. That's what I will do. And then there will be a short intro into the existing project. So if you are finished, it's fine. You could also give your slides already then. But if not, you could do it later. And then this way you would just say a few words on your projects. On existing projects. So this will be something where people will say, I want to do a project on this, or I did a project on that and this, and here's an outline, and the details will follow. So there is a chance to give a short outline for projects. Anyone in the audience who wants to do something of this form on Wednesday already? Yeah, 1, 2? No? Okay, good. So then at least 1. Good. Yeah. And the rest we can do, and I can also maybe invent some projects. Yeah? So the main point is to get more people again on board. I would really be happier about that, because at some point I realized that in particular mathematicians seem to have exams this week. I don't know if there are still mathematicians sitting here. Yeah, are you a mathematician? Yeah. And for this reason I wanted to make this deadline a bit softer. Okay, good. No more questions. Good. Mm-hmm. What we want to do now is talk about model predictive control. I just wanted to make a connection to a field that is actually one of the widest classes of, or widest application fields of numerical optimal control. So why do people actually study numerical optimal control in engineering? Most of the time it is because they want to apply it in a feedback loop. And most of the time they actually close the feedback loop by an online optimization. And then what we do is model predictive control. So chapter 15 is devoted to model predictive control. And that is abbreviated MPC. It's an abbreviation that you will find on a lot of control engineering papers. I was 2 weeks ago at the IFAC World Congress. Okay, it's a huge conference, 3,500 participants, but I would think from, I mean, there are some statistics that are better than just my personal opinion, but roughly 10 to 20% of all papers have something to do with MPC. So it's a relatively large area in the control community, which of course has thousands of other concepts. So if you think of the fact that many other concepts exist, 10 to 20% of all papers is already quite something. And it's probably one of the largest areas of control methods in research. I should not say that people in practice use it as much as they investigate it in academia. So if you want to just control simple processes, let's say you want to just get a temperature here, like here, there's no MPC on that radiator, for example. And if you look at just appliances in the world, like your mobile phone or whatever, probably not so many of them are controlled with MPC. But the more you look at high-value products like chemical engineering, also already engines, combustion engines, cars. Cars are relatively complex. It's worth to invest a few cents more into the controller, and then people start to use model predictive control more and more. Partly driven by, let's say, the high-value industries like, as I said, chemical engineering, that's where it all came from. And now it's also pushed into faster timescales because the optimization gets faster. But let me first explain to you what it is. I think we explained it already, or most of the difficulties have already been encountered. So the statement will now be very easy. So the idea is here, actually maybe I should start by saying, you remember what we do in optimal control? In optimal feedback control, you remember there was this beautiful thing of the Hamilton-Jacobi-Bellman equation, or in discrete time it would be dynamic programming. And in dynamic programming, there was like the dream solution to everything, and that was the optimal feedback control. Yeah? So the dream that we would like to address is optimal feedback control. And optimal feedback control generates for each state a control, so u star of x, yeah, which is the argument that minimizes the next cost over all u plus the cost in the next time step for the j, for the cost to go function. That is the solution of the Bellman equation. Yeah? So that's the cost to go from infinite time Bellman equation. Or we called it, I think, the stationary Bellman equation. Yeah? So you remember that would be the solution to the infinite horizon optimal control problem with this cost. And the argument that minimizes that we call u star of x, and that's like the perfect thing we would like to have. And there was a reason why we didn't actually think that this is practically useful, and the reason is that computing this function j, the perfect cost to go function, is computationally out of reach once the dimension of the system is bigger than, let's say, 5. Yeah? So because then in order to represent and tabulate even this function, it's getting extremely expensive and impossible. So there is an alternative, and the alternative is basically the poor man's optimal feedback control. And that is that we just approximate the infinite horizon problem by a finite one. Yeah? So we optimize on a finite horizon. And maybe I could just, this is a very unconventional view on MPC. I will just give it to you for a minute because I like that. So you could also say that MPC, so the MPC feedback law, x for a given x, maybe I give it, I give an index 0 here just for fun. And I put a bar on top. This will not change anything, all right? But it will just make my notation easier now. So this will be the argument that minimizes over all u. Maybe I call this also u0 now. So it's just changing an index, so there is no problem. The cost that comes from Lx0 bar and u0 plus. And now I add here an approximation to the cost to go, which I would just denote by, and this is a bit funny now, the minimum over all x1, u1 up to u n minus 1 and xn of a sum which runs actually from k equals 1 to n minus 1 of L xk uk. So here is an optimal control problem plus a terminal cost xn, and then subject to here I should put actually the subject to xk plus 1 equals f of xk uk for k from 0 to n minus 1. And of course you could include constraints, and maybe I should directly include constraints, but it will look a bit clumsy. Why I wrote this in this form, maybe I should also maybe remove the bar here, because then this index here will automatically be parametrically depending on x0 and u0 in the first stage, right? So they are not optimization variables on that side. This looks much more clumsy than you might want, but I want to make this connection for a moment, because what we get here is actually a cost that depends on x0 and u0. The minimum of all these of this optimal control problem, and we use that whole cost as an approximation of this form. And of course we will only look into the horizon finite number of steps. So the usual way of presenting this whole thing is actually to just say that UMPC, so the feedback law for an x0, is given by the argument that minimizes over u0, and then I minimize over all the remaining variables x1 up to I put the bar again up to xn. So now I state the standard optimal control problem that we like to have, and then here is the sum from k equals 0 to n minus 1 of the stage cost xk uk plus the terminal cost, and here we have the constraints of our optimization problem, which are xk plus 1 equals f of xk uk k from 0 to n minus 1. So there is no reason to really pull this this first part out of it. The only reason to separate between this min and that min is actually to to make sure that I'm only interested in the first part of the solution. Basically, I solve this optimization problem over all variables, and I select only the, sorry, here's only U1, and I select we do it this way. Then it's really parametrically depending on x0. U0 is not a variable here, and now we basically have the optimal control problem where we eliminated x0 and u0. So you solve this optimization problem, and you get the feedback as a function of x0 by solving the optimization problem online. Yeah? So the idea, solve OCP online to approximate optimal feedback control, OFC. Yeah? So the dream that we cannot reach. And there are some interesting things that I think you can remember from the optimal control discussion that we had in dynamic programming. But before that comes, there's a question.
Yes.
Yes.
So according to the current formulation, x0
Yes.
is still a minimization or a variable that enters the minimization there. Is that
Thank you. So I move it out. Yeah, so it's easy to eliminate that. And this way we will have it correct. Thank you. Yeah. So these two statements are nearly the same. Here I start 0, there at 1. I like this one a bit because it makes the connection between what we do in dynamic programming. And there is some other facts that I would like to point out, but they are not so relevant to what follows. But the one thing that I want to mention is that if you choose E xn to be the terminal to be the solution of the Hamilton-Jacobi-Bellman of the Bellman equation. Yeah? So if you take the last the cost at the end of the horizon to be already the solution, which of course we don't have, but if you would, right, this would imply that for any n, and maybe I should add an index n here because it depends also on the horizon length, right? So to make it sure, so this is like n for the horizon length. Then actually the MPC will be identical to the optimal feedback control for any, n. So interestingly, of course, for n equals 1, we would immediately see it, right? Because then it would just boil down to the formulation above. But if n is bigger, solving an optimization problem will so to say repeat. Because of the Bellman equation, it will just be as if we would have solved the Bellman equation again. Yes.
So just to understand, so U and MPC is just a single scalar or just a single
control.
not
Yes.
a complete control trajectory.
No, exactly. That's why I made this clumsy notation with min and min. Yeah? So I will maybe explain it in more words in a minute, but I think a picture will tell it easier. So if this would be the case, then we would have the perfect feedback law, but of course this will never be the case. So in reality, of course, E is not equal to J. No? So you will choose something simpler, much simpler. And I left out constraints now because in principle from this dynamic programming point of view I could subsume them of course as infinite costs. So it's all in principle in here, but of course in practice we will separate between constraints and objective functions, and that is also one of the reasons why people use MPC, because of constraints. So in reality you could say MPC works as follows. You solve, at a time point k. K, maybe I don't call it k, I call it I. Solve for the current system state. So you need to give an current system state. We call the system state x0 with an upper index I to express that it really is, so to say, at physical time I actually. It's not the optimization time, which I denote here at the bottom. It's the initial value to an optimization problem. You solve the OCP. And now I state the full OCP, and I think I use now the same notation as we have here in the script. Exactly. This is already the full implicit. Okay, that's good. Why not? So you solve an OCP which you could call the following. You minimize over x, z, and u. So we include even algebraic variables to make it a bit more general. We have x, k, z, k, uk plus e, xn. And then subject to the initial value constraint that says x0 should be equal to x0i at the current time point. So we start where we are. Then we have our system dynamics x, now I use here k plus 1 minus f of xk zk uk equals 0. And we also include some algebraic constraints here, g, xk, which could be, for example, collocation conditions. And we also have inequalities, xk, zk, uk. And we could have a terminal constraint. So, and these constraints hold for k from 0 to n minus 1. And so I included now these extra algebraic conditions. This is defining the dynamics. You could think of these as, for example, intermediate collocation nodes, and you solve this problem in all variables, right? So you solve it, and what you do is take u0 as u MPC of x0i. So you basically, or maybe I give it a star. So the first control value of the solution, when you have solved this problem, you give as a feedback control. And this is the way MPC is implemented. So you actually optimize online. So you need to do online optimization. And sometimes online is also used, instead we call it real-time optimization. And sometimes we call it embedded optimization. These are different words for basically the same thing. So online optimization, real-time optimization, embedded optimization. The main concept or the main fact is that at the end, our optimal control software will not run on MATLAB, like on your screen. So you will not be having a human in the loop, but there will be the optimization solver in the background to solve this optimization problem for us. And this will generate feedback. So if you want to embed this into a classical control engineering block diagram, which control engineers like to do, of course, then you have the real system here. The system, for our purposes, has as an input a u, and as an output it outputs the state. So it's a discrete time system in the simplest case. And now what you do is you take the state, you have another system which is our optimization solver. So MPC optimization, and that spits out the u0. So this way you create a closed loop system, and of course sometimes you tell the optimizer something like a reference change, so you might have different desires that you could express and that you could change during the runtime of the algorithm, and here you could say something like the objectives. Like reference tracking and so on. So this is, of course, a very unusual way to write down closed loop dynamics. I don't have measurements and so on, because in reality that will make just things much more complicated. But what we will have is we have the real system that actually takes so we take xi, the state that we have, the MPC that we just defined, xi here. This would be the the control and the state. We plug that into our function f. Now I'm getting mixed between this algebraic notation and the non-algebraic notation, but let me just do the non-algebraic one again. And that gives me x0 I plus 1. So the next physical state of the real system. And that one, of course, will not be exactly what I predict. It will typically be something else. But this would be the nominal closed loop system. Yeah. So please excuse my mix of notation. Maybe I should just have. I put a little tilde here to make this f a bit different from the other f. The other f is actually when you eliminate the z, I could plug them in here already, and then I get the f that I have there. At the end, we have an optimal control problem to solve online, and that's what I want to focus on. Maybe before I go on, I would like to ask if the idea is clear, or if maybe I already add one picture, which is sometimes helping. At least it helped me to understand what MPC is. What you do, so to say, pictorially, is you look into the future while you optimize your system. So you have your model, you optimize the future, and you solve your optimization problem as good as you can. And in the context of optimal control, we could say actually we have a horizon up to 0 to big N. On this horizon, we have some sampling times. And on these sampling times, we could determine an optimal trajectory. We have our initial value. So it goes here, that's our prediction. We have solved that problem. I call this x0i. This is the initial value. We have solved it. It gives us this u0, or this u-MPC n of x0i. So after you implemented that on the real system, you will actually evaluate your real system will move forward. So it will be now at this point in time. And at that point in time, I might be here, but I might also be somewhere else because I have a real system. It might be perturbed. So I'm somewhere in the vicinity, maybe not exactly the same. And basically now I solve an optimization problem on a horizon which is moved forward because my absolute time moves forward and I still look n steps into the future. So now I look into the future by one step more. And I take this as initial value, I solve the problem again, and now the solution might look similar to that one or not. It's definitely different because I appended a new interval here. And it is also usually different because I have a perturbation here. I should just say, if I would have used the perfect cost to go as terminal cost, and if I didn't have a perturbation, then my moving forward wouldn't change the solution. But in reality it does. So then I solve this problem again on this new horizon. So this would be x0 I plus 1. And then I get a new solution which might look similar or not, which gives me new variables for all states and controls. So that is how MPC works on a more pictorial basis. The funny thing is usually people introduce it this way. And that's maybe more intuitive even than optimal control. You just say, I predict a bit into the future. When I drive with a car, I also predict into the future. But I wanted to use the connection to optimal feedback control here because that's actually something very useful to understand that the terminal cost that we have here would be perfectly, we would like the cost to go function, which we don't have usually, but anything that's approximately true to or close to it would be welcome here. Is there questions about the general setup of MPC? Some people have been in a seminar on MPC, so in that sense, for them it's relatively clear, but also the others, I would really like to invite. The rough idea is there. Then maybe I want to say one word about the reality. I mean, the reality is that, and so there are a few things that are different. I mean, the first thing is you see directly this optimization might take some time. So the fact that this takes time makes our system maybe delayed, or we need to maybe approximately solve this problem, and that's what we do actually. So in reality, you will only approximately solve the optimization problem. That's one of the things. The other thing is that you usually don't have the state available. So the state here is usually not really something that your system just outputs. In reality, you will have some measurements, but they are not the full state. So in reality, actually, the picture is extended to something that looks more like this. So you have the system, there come some controls into it. Here's the system you want to control. Here's some measurements that you get out from it. With these measurements and the controls, you will actually generate something that is an estimate of the state, and the module that produces it is called a state estimator, and this could be optimization based itself. And with the state estimator you get an estimate of x, which we call only x hat usually, and this one is fed back into the MPC optimizer. And this one might get some desires. So this is like the usual setting. And then you really see, as a control person, now you see, it's really the system has inputs and outputs, and all the rest is actually our controller, but it's now the state controller, which first estimates the states and then optimizes the future. Okay, so that's, let's say, the framework. Why do people do model predictive control? And I think I want to directly jump to a few algorithmic strategies that are used in order to make the optimization fast. And that's what this lecture should be about. So I really want to focus on what we do inside this optimization, because here we are dealing with optimal control and numerical optimal control. So let us see how we can solve the problem fast. There is one obvious way that people always think first, and it's not the only one, and it's not necessarily the best initialization scheme, but if you think of one thing, you look at these pictures here, you say, maybe the most logical thing, if I have one solution and I want to actually initialize the optimization problem of the next one, and we know initialization is very important in Newton type method, then what we should do is maybe take this solution that we have already on our horizon and shift it, so to say. I mean, shifting means that we take away the first interval so that we have now the correct variables at the new time points, right? Because now everything, the horizon is moving forward basically from here to here. So then we just leave the variables where they are physically, so to say, physical time. That means in index time in our optimization problem, everything gets shifted back by one index. And here at the end, I mean, because the last interval didn't exist in our horizon, we have to invent something. And there is one, you could copy the last interval, or there's some other smarter ways to add something. But that is what we call a shift initialization. Yeah? So there's an obvious thing that one could use, shift initialization. Yeah, so that you basically have your solution, U0 star, our solution to one problem is x0 star, U0 star, x1 star, U1 star, and so on, up to UN minus 1 star and xn star. And then you shift that, and shifting means I only take these variables here, move them, so to say, by one time step, and now I give the first variable this value, right? And then at some point I have UN minus 1 star, and here I will have xn star, and now I'm needing something like a UN, I call it bar, because I need to invent it, and an xn plus 1 bar, right? So these variables I need to append in order to get the same dimension, but I basically shift everything by one time step back. That's why we call it a shift initialization. Yeah, and here we have we need to invent. Yeah, so we need to invent these things, and that's something non-trivial. And there is actually the other initialization that you could just use if you have one solution, and the other is what we could just call warm start. Maybe I call it a simple warm start, because it's just simple, and this, it's even simpler. It's even more obvious. What you could also do is you could just take here on the lower line x0 star, u0 star. So you don't account for the motion of time, even though you know that you move in time, right? So you could just leave what you have in your optimization variables already in your optimization problem, and very often this is equally good. Yeah? Or sometimes this is even better. I should say every problem is different, and we can discuss about it in detail, but for the setup that we have here, which is not depending on time, so none of these functions or systems is depending on time. For that setup, if you have a short horizon, the warm start is usually better, because the solutions look very similar, even though they shift forward in time. If you have a very long horizon, actually the shift would be a bit better. So I will not talk so much about how to choose these objectives. That's the subject of full courses in control engineering, but I want to focus on the numerics. But did you have a question? Was it about the weights? Okay. Yes, okay. Maybe the first thing is the most crucial question is actually how do you choose this objective here, and yeah, how do you choose the constraints? The constraints are maybe easier, because constraints are really the things that we read, that we need to determine. So very often you have bounds on your controls and so on. So they are the same constraints that we have in optimal control all the time. On the objective in MPC, very often people use tracking costs, so something like least squares. And maybe I should also say that the origin of MPC is like an extension of LQR. We have discussed the linear quadratic regulator. We know that if the system is linear and there would be no constraints and the cost is quadratic, we would get this perfect linear quadratic regulator. But once you add even to a linear quadratic problem the constraints, we will end with a quadratic program, right? And then the feedback law gets already significantly different from LQR and extends it. And in this case, the perfect cost-to-go function would be already difficult to compute. I mean, even for linear systems, but with inequality constraints. Okay, so very often you want to track some steady state and you want to just respect constraints. So that's one of the most typical applications of MPC, but also there are others. And maybe one remark is that sometimes people use here an economic objective function which directly tries to maximize profit and so on, and then that's what people call economic MPC. And if this is just a function that is tracking some reference point which is usually computed before as the optimum of something, then we call it tracking MPC. But I don't want to talk about the formulation, but in this lecture I want to talk only about how to do efficient optimization, and I want to give an outline already now. Maybe it's better to do the break before, and then we really go into the real-time optimization strategies. So what do we do in order to solve this optimization problem fast and efficient? Okay? So 10 minutes break. We start 10 minutes past 3. Okay, we continue. Okay, so what we want now, we want to discuss how to solve these optimization problems fast. Yeah? What can we do, or what can we do to deal with the problem that while the real system runs, the real system evolves in time, we want to solve an optimization problem, and this optimization problem itself takes time. Yeah? So that is like the dilemma we want to address, and some strategies I want to discuss just in words because they are relatively quick to explain and they are the general concepts that we always have. So this is section 5.15.4, and this is real-time optimization strategies. Yeah, so the question is how to deal with what we could call the online dilemma. That ideally we would like to have our solution in no time, yeah, but in no time we can probably not get a very accurate solution. So that the solution algorithm needs time. So that's what I call that's a kind of dilemma in which you are when you deal with MPC. So the first thing that you can think of is do as much as you can offline. So we call that offline pre-computations. And if you do offline pre-computations, of course the most extreme would be you somehow pre-compute your U MPC. You could try to somehow pre-compute your complete feedback law, but then you need to store it, and then we are back at the curse of dimensionality. So you will not use it for higher dimensions. So that's like dynamic programming. So you will probably not do exactly that. But what you could do is you could do a few things in order to get a short horizon with a relatively good approximation of the terminal cost, which is maybe already based on some pre-computations. You can also do some other things that you could do, which is related to factorizing some matrices which you know are constant. Huh? Factorize some constant matrices before. Huh? Factorize some matrices, some fixed. That's something that we sometimes do, fixed matrices. That's also something you could do offline. Sometimes we also do some things like you need to compute derivative code, right? So in Casadi, for example, you construct a tree, then this tree will be processed, then it will somehow construct a reverse adjoint Jacobian evaluation and so on. And these things lead to relatively long C functions that you could also just spit out as C code. And so you could actually use what we call code generation. That's basically doing something offline that will make it faster to do the online thing. So basically the philosophy is do everything that you can do already before the problem is actually formulated online, do everything offline. You could sometimes also do some model simplifications or whatever. That is something you can do by hand. Huh? So you really look at your code to make things really as efficient as possible. So that's just offline pre-computations. It's not particularly it's a lot of different things. But then there are some other things which I also want to mention. One is delay compensation. So this is very intuitive also. So in model predictive control, like in all model-based control techniques, we have a model and we predict with this model. So when we know that we cannot solve our optimization problem in a finite time, but we know already we need maybe 5 sampling times to solve it, for example. Yeah? Then what we could do is we could take our state at this time, predict where the state would be in 5 samples when we apply the controls that we have to apply anyway. Some controls we have to apply, right? So we take now the decision we will take these old bad controls, but anyway, we apply them. With this state, after 5 samples, we will be there. And for this state, we start to solve now the problem. So now we solve an optimization problem for a future time. And when we are already solving it, then we will have arrived, hopefully, in the vicinity of where we predicted we would be. Yeah? So it's something quite intuitive. you predict where you will be and you solve this problem already. I will not say more words about it, delay compensation by prediction. Maybe the only thing I have to warn, of course this is still not giving you feedback. I mean, you still have a long feedback delay. So if your model is wrong, or you get disturbances in the meantime, you will have solved a problem that doesn't correspond to your current disturbed state. So this doesn't resolve everything that we need. And there's another thing that you can do here, and this is what we call a division into a preparation and a feedback phase. So what you can also do is you can do something that you can only do online. You prepare yourself to be fast when you get actually the state estimate. So you divide all the computations into something that's a bit like offline, but it's not really offline. It's something that you can only do online. So you try to, for example, in a Newton type iteration, you already prefactorize some of your current matrices and so on. But then at the end, you wait until the x0 comes, and then only you solve a linear system. And then this gives you something that we could call a feedback on this latest x0. So we... I want to discuss this a bit more later, but I already division into preparation and feedback phase. So what you do is prepare yourself for the next feedback moment. For example, by pre-solving something like a problem that you will expect for next feedback moment. That would be the first thing you do in this during one sampling time, right? That's taking a long time, and then you take, you measure or estimate the new state. x0i, the state that we get it, and then in a short, this would be the preparation phase. And then you measure this, and after you have measured it, you compute the feedback. Where you so to say, approximate, you say an MPC, an approximate MPC of x0i is now computed. It's not the perfect one, but it's something that is based on all the computations that you did before. This could be, for example, typically it's a linear system solve. So as opposed to linearizing, pre-computing, sometimes it's also a QP solve. So these would be is one other trick, preparation and feedback phase. So you do something that, maybe on the timeline, here is one sampling time. This is another sampling time. Here is where you get the xi plus 1. Here is where you got the xi, and here is where you get xi plus 2, right? So what you do is you prepare yourself in this time as much as possible to the future state that comes here. When it really comes, at that moment you take a quick action, and hopefully after a very short time, this would be preparation phase. You have prepared yourself, and then you take the measurement. That influences your feedback controller, and then this is the feedback. And after you have performed the feedback, you already apply the new control. So what you will do is actually you will apply one control in this whole time. This control is based on that state. And after you have performed this feedback phase, you can apply the next control for a while. So you get only this little delay from the measurement of the state to the next control. So that's now a delay reduction, because it's not like the full solution that you you solve, so to say, like here, you predict maybe, but then you solve very accurately your whole problem. What you do here is actually you prepare yourself, and at the moment that you measure the xi plus 1, you do something quick and dirty, and you get some feedback which is better than nothing. Yeah? That's the idea that we would have here. Let me just list some other things. Some other idea is that you iterate while the problem changes. So if you think of Newton type optimization, it's all iterative, right? So usually you do a few iterations, and after a while you think, now I'm converged, this is the solution, I stop. What we do here, we could also say we just do one iteration of any type of iterative algorithm that we have. But after we have finished one iteration, we actually ask the real system, at which state are you now, and modify our problem while we are iterating. Yeah, so you iterate while the problem changes, and so basically you shift, so to say, the point of view. You say, I have an optimization algorithm, and this optimization algorithm is, while it's iterating, always getting modified data. This is where I want to conclude this little collection of ideas. And I want to go a bit more into details for the nonlinear Newton type optimization algorithms that we have presented in this lecture. But first there is a question.
Yes.
Yeah.
We discussed the approach of multiple shooting.
Yes.
So what I'm missing here is any parallelization approach.
Yeah, okay. I could mention it. Let's just add it. You can parallelize. It's like, yeah, it's not typical. I mean, this is of course something that you should also do. Yeah, and you can also, I mean, yeah, this is not specific to online. I mean, that's making every algorithm faster, but it's right. Yeah.
Okay, but
yeah.
is that like
sorry?
Does, for example, like the opt have the capability to?
Yes, of course. Yeah. All algorithms can also be parallelized, and some easier than others. Of course, I should also say, you on the same line, you could also adapt to your CPU. Yeah, so you could actually make some smart things in order to really exploit your CPU in the best way, like cache management and so on. That's what also compilers sometimes do, but you can try to do it better than the compilers. And that's what you can also make to make things faster. But I should say, these are not, they would also affect an offline algorithm. I mean, already on your desktop, you can see that they make your things faster. That's why I didn't list them, but you're right. It's actually also important in practice to make your thing as fast as possible. Other questions? Yeah, or maybe more ideas even, yeah.
There exists some hardware that is specialized for optimization, like there is hardware for signal processing?
Yes, that's a very good question. MPC is not such a huge field as signal processing in general, that there exist really chips that are designed only for MPC, with the exception of some FPGAs, of course. But they are, of course, not really chips for that application. So people use other domains. I mean, like GPUs are sometimes used, FPGAs, and then normal digital signal processing units, and typically microcontrollers. Yeah, microcontrollers are like the things on which a lot of MPC needs to run. Yeah, fortunately a lot of microcontrollers support also basically plain C and double floating point, and so you can actually run basically the algorithms we presented here on a state-of-the-art microcontroller. Yeah, more questions? No, then I would go into the field that we actually need to address now, which is actually parametric nonlinear optimization, because that's what we basically ended up with. We had an optimization problem which depends on some data. Yeah. So let me introduce you to parametric nonlinear optimization. And if you remember the problem statement that we had, there was an optimization problem that depends on a lot of data. There we had basically x0 minus x0 bar equals 0. And then the system constraints here, xk plus 1, f of xk uk, sorry, here, k from 0 to n minus 1. And the thing that really changes in our problem is the initial value. And for each initial value, you would like to find the solution. So I can summarize this whole problem in a simpler form, or not in a simpler form, by bringing everything into one optimization problem. I could just say what I have. What I would like to do is I want to find the solution of an optimization problem with some data W. W are my optimization data, and I have some function that in principle depends on some parameter, P I identify with x0 bar, with a thing that changes, which is here. And I have some constraints, G of WP equals 0, and some inequalities of WP smaller than 0. So this would be an optimization problem where we get a P in. P is the data, yeah? And what we get out is the optimal solution, W star of P. That's what we would really like to have. That's the dream of MPC optimization. And of course, this this G is the concatenation of all these constraints already. So it's the optimization problem after direct transcription. Oh, sorry, not direct transcription, any direct method. This is a parametric NLP, nonlinear program that comes from a direct method. It could be from single shooting, from multiple shooting, from collocation, anything. But it will always have this form. So that's what we would really abstractly look at. And I think I will better visualize it a bit. I think I want to go into some maybe I first give you a picture and then we go on with a little bit of algorithmic ideas. So the first thing is, if you look at this W star as a function of the parameter, then this will be a map that might be continuous, and usually it is. It can also be discontinuous if you get some minimizers that move. In particular, if you would globally minimize, then you would actually have possibly jumps. If you only track one local minimum, then it might actually at some point disappear, and there could be a lot of nasty things. But in the nice cases, and for example, if we would have a convex parametric program, then these things would be continuous and nicely defined. And you could think of this as a differentiable map, something like this, right? Which you can implicitly define via the optimality conditions of that optimization problem. There is, of course, one interesting feature already due to the inequalities. You remember, inequalities can be active or not active. And if they are not active, they will not influence the solution. Once they become active, they will influence the solution, and they will become binding, so to say, in the KKT system. And that turns out to have an effect on the solution. It will actually be non-differentiable at the points where the active state changes. Simplest example is something you change an initial value to an optimization problem. When you start, for example, at 0, everything is nice, the control answer is 0. Then you move your initial value, and the optimal controls in your horizon, they will react, but they will not become active constraints, right? At some point, your control might saturate. I mean, you move further your initial value, and the optimal controls at some point hit the bound, and at that moment they don't move anymore. So at that moment you will get a change in the slope, and for example in that case it could just remain constant for a while, right? Then maybe some other constraint gets active or whatever, and things could move out again. So at these points there would be active set changes, and active set changes will incur non-smooth changes in your optimization problem. So this would be active set changes. So they lead to some non-smoothness. That's an interesting thing. But what we could do first is we could look at the point where everything is nice. So if everything is nice, we can get some solution information from just looking at this at the optimality system, and we can try to compute the tangential predictor, or the tangent to our solution manifold, and that's one thing that I want to do. And in this case, I think I want to do it in a very simplified setting, and this simplified setting is relatively simple. Yeah? So assume for a moment fixed active set. Yeah? That means that we are actually on some of these smooth parts. Yeah? And then the optimality system, including all the multipliers of the active constraints, we can summarize it as this: R of Z and P is equal to 0. Yeah, so then the KKT conditions for the fixed active set, they would could be written in this form. So you could just say we have a root finding problem, Z, finding the equation Z. Yeah, Z would be primal and dual variables, and P is still our parameter. And what we would then get, I mean, R is a function that maps from R n Z and R n P to R n Z. Yeah, and the optimal solution of this would be now Z star of P. And Z star is now not only the W star, the optimal values, but it's also the optimal multipliers and so on. So just in a larger space. And that is actually defined by the implicit function theorem, right? So what we could now do is we could just compute at some point at a solution the derivative that we would get from the implicit function theorem. And we know that this would be given by dz star by dp at some point p. Maybe I call it p bar, yeah, because I want to evaluate at some specific point for the moment. This would be given by minus the derivative of dr by dz evaluated at z bar and p bar. Yeah, z bar is actually the solution at p bar, yeah, so it's the perfect solution, to the minus 1 times dr by dp at the point z bar, p bar. That is what the implicit function theorem tells us. Maybe you remember the implicit function theorem? Yeah? Good. So what if we look at that, the interesting thing is that this matrix is something that we nearly have already in Newton type optimization methods. It's actually the inverse of the KKT matrix. And so if we are at some solution point here, we could actually, and this is already one of these feedback phase predictors, we could actually evaluate all our derivatives here and then try to get this point when we have the move from a parameter p bar to a new one. We could use this one instead of the true solution here. And that is one of the possible algorithms. So I call this p plus, so it could be the next p. So one way to a tangential predictor is what we call a tangential predictor of what? Of z star of p plus, of the new parameter, based on z bar and p bar. I mean, if you are at a solution z bar and p bar, and you would like to have a tangential predictor, then you could actually get something that is the first order Taylor series of this thing, right? So you could take z star of p bar plus dz star by dp at p bar times p plus minus p bar, and that is actually a first order predictor of the true solution at this new point. That's the first. How does that? Where would it evaluate to? It would actually evaluate to the system which would be z star of p bar minus dr dz z bar p bar to the minus 1 times dr dp at z bar p bar times p plus minus p bar. Okay, so this is like what we would have here. And this is a formula that looks really similar to a Newton iteration, and I want to show you actually how we can get this formula nearly for free when we just look into a Newton type framework. So we remember that formula, and I just take now a very different point of view. I would just say I try to generalize the Newton idea. Maybe I should first say what's the problem with this formula. So the problem with this formula is that I assume already that I'm here at this point. I assume that I'm exactly on the solution manifold. In reality, I might be at a point which is close by, but it will be very unlikely that I'm really on the solution manifold. So I will never be exactly here. So can I get something that's nearly as good as this point by just starting at a point x bar, p bar, which is not actually exactly satisfying the solution? And in order to get it, I want to actually think of the following. So I just say, what if z bar p bar does not satisfy? Yeah, so that's actually, when would it be a perfect solution pair? It would be a perfect solution pair if this r z bar p bar would be 0, right? So then it would be a solution pair. Then it would have, this relation would be true. But if z bar p bar does not satisfy it, then we just let's do a Taylor in both variables. Taylor in both z and p. And what would be a Taylor expansion of that? It would be actually r of z bar p bar plus dr dz at z bar p bar times some step in z, so let's call it z plus minus z bar plus dr by dp, also evaluated at the point where we are, and that is multiplied with p plus minus p bar. And this is what we want to have 0. So this is a Taylor expansion in both variables, and now I could try to invert that whole thing in order to get a new value for z plus, because z plus is the thing that I would really be interested in, right? So p plus is given, so these the difference in the parameter is given. Of course, this is also given, and that is desired. I would like to find the z plus which satisfies a linearized version of my equation in both variables z and p bar. And now I will just do a bit of tricks. I will not many tricks actually. I will just bring that whole equation to z plus. So what will it be? It will be z plus is equal to z bar, yeah? And then I pre-multiply everything with a minus 1, and that will give me here a minus dr by dz at z bar p bar to the minus 1, and now I evaluate it with r z bar p bar plus dr dp at z bar p bar times p plus minus p bar. Here I close the bracket. So now I have, this is the same formula, just reordered, and that looks very much like a Newton step, right? It looks like what we would usually do in a Newton type method. We would just evaluate these two things, right? And that's it. And the difference now is that we get this predictor step here. So that's the that would be a corrector, Newton corrector, normal Newton corrector. And this is what we would, which leads to a predictor step. It's actually the tangential predictor. And now let me just compare the two formulas. So what we get here, this would be, of course, also, this would be a kind of Z plus. Yeah? If we had a solution, yeah, then the Z bar would be equal to that one. Yeah? So then this would be already the same. If we also had a solution, then this would be the same expression that we have here and here and here. And if it was a solution, this term is 0 anyway. So if we would have at a solution, yeah, so for Z, for the case that R of Z bar and P bar is already 0, this boils down to what I call here maybe star. So the formula star, but it is more general because it's applicable to anything that's also not exactly a point. Maybe I should also, maybe I say, but it is more general. Is more general. There's another special case. If you think of it, if you wouldn't have a change in the parameters, so if this P plus and the P bar would be identical, then this term would be 0. We wouldn't care about that whole thing. And then it would just be a typical normal Newton iteration. Yeah? For P plus equals P bar, it equals a Newton iteration. So this gives rise to a scheme that we can just use now to solve a sequence of parameter values. I mean, there's an algorithm to solve or to approximate solution for pk plus 1 and so on. So imagine that you have a sequence of parameters and you want to find an approximate solution to that. And one way is to always do one iteration of this form where you actually keep a solution guess for the z's. Yeah? So you start with a z0 and a p0, so to say. I mean, something at the beginning. You initialize. And then you set k equals 0. And then you iterate for k from 0 to k to infinity. And when you get you get first pk plus 1. So when you get that pk plus 1, you get it as a measurement actually from the real system, right? So you get the initial value of your optimization problem. When you get that, then you generate the next guess. You generate an approximate solution. By this formula. So you just say zk plus 1 is equal to zk, the old iterate, and then I just copy this formula here. Minus dr dz at zk pk to the minus 1, and here I evaluate r of zk pk plus dr dp at zk and pk times pk plus 1 minus pk. So this formula delivers an approximate solution to zk plus 1. So maybe what I should say here, note that zk plus 1 is similar to z star of pk plus 1. So it's of course similar in the following sense that we just discussed. If you started on the manifold, it would be a tangential predictor to the true solution, but it's actually only one linear system solve. And here you can already see what could be done in a real-time iteration context or in a real-time context. You would actually say, you get the pk, and if you get the pk, you need to solve the system. Basically, you need to have this factorized matrix multiplied with these derivatives and so on. And if you look at it, there's nearly nothing that depends on pk plus 1. I mean, only here the pk plus 1 enters. So you could actually pre-factorize this matrix, evaluate that function. Also, this derivative could be computed before. So there could be a lot of things that you could do in what we call the preparation phase. And only once you get this pk plus 1, you do the last step. So what the outline of that algorithm would be, if I just depict it here on this graphical board, so this would be P, here would be pk. Yeah, so then maybe let me just, this could be now the smooth solution manifold. Yeah? So that is Z star of P. And then you are somewhere at a point, sorry, this would be the axis, this would be Z. Yeah? So these would be the solutions. Yeah? So this would be the set where R is 0. And now I'm at some iterate here. This could be ZK. And the linearization of the Taylor series that I have here at the top, that will give me, because it's an affine function in both Z and P, it will give me some set, maybe this one, maybe I think I will draw it in red, it's better. Huh? So this will be the solution set of this linearized version of my equation. And if I do my next iterate, once I know the point pk plus 1, I would select that one as zk plus 1. Yeah, so that is the algorithm. Maybe I should say it looks a bit perturbing that we have here, this doesn't go through the point zk. It doesn't because of the Newton step, because this r is not 0. Yeah, so this would be the corrector part of the step. And this would be as a predictor. And if I wouldn't have, if the pk and the pk plus 1 would be identical, then I would only have the corrector steps. And if I would be already on the manifold, then the corrector step would be 0, and I have only the predictor steps. So this combines basically a Newton method and a tangential predictor into one iteration. I just evaluate these derivatives and this residual, and I do one Newton step. So that is the basic algorithm explained in the case that we don't have inequalities. And now we would like to generalize that whole thing to the case where we have inequalities and where we have active set changes. And for this, it turns out that it really helps to interpret the Newton step again as a quadratic program. And now we need to, I think, what should we do? I think we will discuss it really in a bit more detail next time, because it's too important to just do it at the end of a lecture. But I just wanted to already outline that the idea that we have here, that we get basically a kind of corrector and a predictor step by solving one linear system, we can generalize it. If we are able to solve one QP, one quadratic program, then we can actually generate an algorithm that is inspired on the same ideas, but which is able to deal with these active set changes in a very natural way. And it's similar to SQP, and we will explain it in the next lecture. So maybe I better use, because I got a bit too enthusiastic, I realize, I better slow down, and I try to digest what we did here and close maybe gaps that have been left. So maybe the first question is, did I explain sufficiently well what I mean by this R of Z and P? So do you have a rough idea, or not a rough idea, but I never wrote down what it is, right? It could be, as I said, it would be the optimality system of an optimization problem like this one. Yeah? So it could be something like R of Z could be something like the Lagrange gradient being 0 and the constraints being 0. Yeah, so that would be what I have in mind. And Z could be W and lambda together. So that's the first thing, just to be sure that we don't have that gap. From that interpretation, you already also have the fact that this linear system solve can be interpreted as a QP solution. But we will do that next time. And yeah, maybe to just get I think maybe the most important formula and the only one to really remember is the one here at the top. And it's extremely simple to remember, right? The idea is if we have a parametric parametric root finding problem, which lives in two variables p and z, then let's linearize the function in both variables at the best guess that we have, which would be here. And of course, this picture is a bit too simple because p is high dimensional and z is also high dimensional. So it's of course a very simple picture, but the main property will still be satisfied, namely that if you think of 2 dimensions now, the function r, the function r is something that is positive on one side. Let's say here it's positive, and then it intersects with the blackboard at this border here. This is where r of z and p is equal to 0. That's what this line means. And on the other side, it would be negative. Here it would be positive, and here it would be negative, right? So that's what defines the z. And the linearization of our function r, because it's a linear function in both z and p, it will have an affine solution set, which is actually this red line here. So that's the solution set. Maybe I should depict it. So that is the set of all pairs z and p that satisfy the linearized equation. That means r of z bar, here it's k now, right? Zk, pk plus, and then the derivative dr dz of z minus zk plus dr dp times p minus pk. And I omit the index, of course, this is evaluated always at the same point, equals 0. So that's the solution set of a linearized equation that delivers us something like a tangential predictor. And once we know the value pk plus 1 that we actually on which we want to evaluate that line, we could just plug this into this case here. We evaluate this vector here. This is a vector. Make one one linear system solve with this matrix, which we could have prefactorized before, and then we get the new guess zk plus 1, namely this value here, which is of course an approximation of that one, but this is something we will never be able to get. And actually, in the next iteration we will probably have another value here, pk plus 1, pk plus 2 will most likely be a new parameter already. And then we would actually make the same picture at this point. So we will linearize here, get a new solution approximation, which is approximately tangential to this thing. So it will be maybe something like this. And then we might get at this point at the end. So at this point, we would, now I draw it in white, we would linearize our system again. We will maybe get this solution set, and then we might be here. So we somehow try to always be approximately tangential and try to find the true solution. But because we change our problem, we will always just be close to it, but not really be on it. Okay. So I got too enthusiastic again. So slow down. What other questions could you have? So the basic outline of this algorithm is there. So that's the main idea here. We solve one linear system in each iteration, and we basically track our solutions while we do it. It's a form of, it's a bit like warm starting, but it's a bit more because we get these tangential predictors. If we wouldn't do that, I mean, if we wouldn't include that value here, we wouldn't get the tangential predictors. Yeah? Already dropped. Yeah? No.
The step that you drew, like, I understand the red line, of course, is going down.
Yes, yes.
And then from the green point, the linearization point,
Yeah.
you drew the point going to the right. I would have expected it to go down.
This one?
Yeah. Then the next step you mentioned
Here?
is on the right. Why is it not going down? Are we trying to find the middle?
No, we try to find the points here on this. I mean, the perfect solutions would be this, and this, and this. And then maybe here would be the next point. So this would be the thing that we would really like to have, but we will never have it. Because we are only close to the right solutions, and yeah. And so what we will do next time is we will generalize that idea to the case where we have active set changes. So where we have these corners, where one constraint becomes active and inactive. And we will see that we get that algorithm by just solving QPs in each iteration. Okay, so let's stop for today, and I thank you very much and see you on Wednesday.